Okay, critical points and intervals of increase and decrease. That's our goal. We want to work a couple of these problems, and we have all the tools now to solve this problem. Okay, so critical points. What's the definition of a critical point? It's a place where your function has a horizontal tangent line, or it's non-differentiable. Again, for us, almost always, all of our functions are going to be sort of nice textbook polynomial functions. Critical points are where you have a zero derivative. Okay, so we don't have to worry about that non-differentiability. This function is differentiable everywhere. And so critical point is where your derivative is zero. So we're going to take our derivative and set it to zero. And that'll give us x values, which make that a true statement. And therefore, those x values are our critical points. So let's take our derivative. We'll see that we have three things separated by plus signs. So we're using power rule, constant rule, and sum rule. Or just going ahead, we've done enough, we're just taking derivatives. So times the power down a power, so 4 times minus 3/4 gives me minus 3 down a power. 3 times 1/3 is 1 down a power. Derivative of a constant is 0. So we have this equation. Negative 3x cubed plus x squared equals 0. We need to find values of x that make this a true statement. So again, here's where we get to review stuff from the pretest, from pre-calculus, from algebra, from previous classes you've had, where you had to solve an equation like this. And what you typically did was you tried to make it into an easier equation to solve. It's hard to just look at this and see a value for x that's going to work. Now you might try the guess and check method, which is, hey, what if x is 1? Does that make this true? If x is 1, I have minus 3 plus 1 is minus 2, not equal to 0. So no, that doesn't solve it. But maybe you see x equals 0. That'll solve it, right? 0 plus 0, 0. Yeah, so x equals 0 right away just by looking, by inspection. We know x equals 0 is a critical point. But we can also get that x equals 0 by following a very sort of algorithmic formulaic way of solving this equation. And typically, because you couldn't just look at a cubic equation and find which values make it true, you tried to factor to make it simpler. And the idea of factoring was to split it into easier pieces. In this case, I can factor out an x squared, and I'm left with a minus 3x plus 1 equals 0. Then the whole point of factoring, again, you could check distributing that you get the same thing you did your factoring, right? The whole point of factoring was that you can set each factor, and they're simpler factors, to 0. So I have x squared equals 0. So that's one equation to solve. And the other equation to solve is this linear equation, which is the easiest type of equation, right? And even though this is a quadratic equation, this is a really easy one. This one tells us x equals 0. Okay, that's the critical point we already found. And we have to solve this equation, and we see that x is 1/3. Right, just doing some algebra, moving things around. So we get two CPs, 0 and 1/3. Now again, you could check that those are CPs visually. So you could go to a tech tool, and maybe let's just visualize that together. And it'd be a good thing to pause your video too and make sure you can do it. All right, so I'm going to go to Desmos, let's say. Whoops, Desmos. It's calculator. Enter in our function. Our original function was minus 0.75 x cubed, no, x to the 4th, plus, we'll do this as a decimal, 0.33, just because I don't feel like fooling with the fraction. On this one, x cubed plus 0.25. Here is our function, and let's zoom in a bit. And do we get, it's really kind of level there, let's see. All right, so let me maybe zoom in even more so we can see. it's saying at 0 right here, there's a horizontal tangent line. And then it does seem like it's very hard to tell, very subtle, but it seems like it rises a little bit and then drops back again. And it seems like right here around 1/3, there is another leveling point, a horizontal tangent line. Okay, so you can see a little bit better there. Very flat there. That's a CP, a horizontal tangent line. And then over here at 0.33, again, yeah, it does rise up a bit. I have to zoom in even one more time to see. Okay, there we go. Here's 0.33, and that is sort of the horizontal tangent line, a bit of a peak there, and then it levels off right there at 0, drops again. So because of the coefficients on that, that one was really hard to tell the difference, right? All right, so visually we got to check our CPs, and then the next thing we want to do is our intervals of increase and decrease, and this is the new part for us. So intervals of increase and decrease are only going to change in between your CPs. So it's a really easy algorithm to find these. So let's put our CPs over here. X equals 0 and x equals 1/3. Make some room. And then I'll show you the page in your journals that we're working from. Increase and decrease is the title, increase and decrease algorithm. And then there's these algorithm pages that have step-by-step how to do something. So you can think about it step-by-step, or hopefully once you've done 1 or 2, you just think about this picture, and that's usually enough to jog your memory as to how to do this problem. Because we want to go for understanding, not memorizing, but I know some folks like to have this step-by-step. That's how they've typically done math. Okay, so there's a problem work there on that page, another nice example. You'll get to practice a couple here on this page, answers at the bottom. And so we're going to do a different one, this one here. We want to find the intervals of increase and decrease. We already found the CP, so we answer the first half of that check. Now we're going to do the intervals of increase and decrease. And they only change from increasing and decreasing, right? Think about riding a bike on this function, right? They only change from increasing. I'm going to shade everywhere I'm increasing on this. Uphill, uphill, downhill, uphill, uphill, pedaling, wee, downhill, heavy, hard to pedal, breathing heavy, downhill. So everywhere that I've shaded is increasing. And then where are the critical points? In this case, every critical point happens to be an extreme, a max, or a min. That isn't always the case. Remember our counting example? Y equals x cubed has a critical point right here. So it's possible, but I didn't draw one here. Every critical point does happen to be a max or a min, and every critical point, notice, is the only places you can change from increasing to decreasing or decreasing to increasing. Either way, the change happens at a critical point. And that's why what we're going to do over here with our f prime line makes sense. So the steps of increasing and decreasing are to find your critical points. We've done that. Put them on an f prime line, which is a number line. Label it so you remind yourself it's the f prime, the derivative line. Make sure you put your critical points, their numbers, in order, like this is a number line, right? 0 comes before 1/3. Those critical points divide this number line into 3 intervals, really going from minus infinity all the way back here to 0, and then this little one from 0 to 1/3, and then from 1/3 all the way up to infinity. Once you've done that, again, you've divided this into 3 intervals. You're going to pick any point you want from each interval, and you're going to plug it into the derivative. So over here, I'm going to pick, doesn't matter, but to make it easy, I think the arithmetic will be easy if I try -1. And again, I'm just reminding myself I'm plugging into the derivative. That's the key part. And then here I need to pick something maybe like 0.1. Right, something between 0 and 1/3, which is 0.333, right, repeating. And then maybe 1 over here, because that should make the, oh, I forgot to put the prime, right. I'm going to pick a point from each interval. I'm hoping I pick ones that are easy to plug in, but it doesn't matter. You could try -100 if you wanted. You're going to take that and plug it into the derivative. So I erased that. We had already computed our derivative. Let's put that in here. F prime of x was let's see, minus 3x cubed plus x squared. And so I need to take minus 1, plug it into the derivative. That'll be minus 3 times minus 1 cubed plus minus 1 squared. So that's going to be minus 3 times minus 1 is a positive 3, plus a 1 is 4. I don't really care about the value. What I care is that 4 is a positive number, which means my function has to be increasing. So what this is saying, when you say f prime of negative 1 is 4, because that's positive, it means at negative 1, the function is increasing. But I also know on that entire interval, from minus infinity up to 0, it has to be positive. Every number I would try, if you were to try negative 2, negative 3, negative 100, negative 200, every time you plug in, you get a positive number. And that means this whole section, from minus infinity up to 0, is increasing. And sometimes this is also written this way, in interval notation, minus infinity to 0. And then we're going to do the same thing with our test point to figure out between 0 and 1/3. Is it increasing or decreasing? And we're going to do that by plugging in, we decided 0.1. So now I need to figure out the derivative at 0.1. So that's going to be negative 3 times 0.1 cubed plus 0.1 squared. So a little bit of decimal work, or get your calculator out, and that's going to be negative 3 times 0.001 plus 0.01. So a tiny thing is negative, a bigger positive. This is going to turn out to be positive. So we're increasing from 0 to 1/3. One more interval to try. We need to plug into the derivative, positive 1. We'll have negative 3 times 1 cubed plus 1 squared is negative 3 plus 1 is negative 2. Not so caring about the 2 part, but definitely care about the negative part. Because it's negative, it means that x equal 1, it is decreasing. And any other point I would have tried in that same interval, I would have had the same conclusion, that is decreasing. So our function is increasing on these two intervals and from 0 to 1/3. And then it is decreasing from 1/3 to infinity. Right, so this number line divided the domain into 3 sections. I picked a point from each section, tested whether the derivative, which tells me about increasing and decreasing, was positive or negative. The reason we don't include the endpoints here, because those endpoints were critical points. Your function at a critical point, the derivative is exactly 0. So it's neither increasing or decreasing there. All right, let's go back to our tech tool just to make sure the picture makes sense for us. And we didn't do any arithmetic errors. So share the screen. Okay, so we were in a very zoomed in view, but let's just, hopefully you can see these numbers down here at the bottom. We went from minus infinity all the way up to 0, and we said we were increasing. And then from 0 to 1/3 was the next interval, and we're still increasing ever so slightly, but all the way up to 1/3 right here, and that's the peak. And then we start going back down and we're decreasing from 1/3, 0.33, all the way up to infinity. So I'll zoom out a few times. Again, that wasn't as clear when we zoomed out, but you can still see increasing, 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 still, even though it's hard to see here, but it's still increasing until right about here, and then drops to be decreasing. Okay, let me make sure I covered everything on that one. And then once you've done that, you could still do additional review of like finding equations of tangent lines at particular points on that curve. In fact, let's do one of those right away. Let's say, to extend this problem a little bit, there are intervals of increase and decrease. And just to review, find the equation of the tangent line at x equals 0 and at x equals 1, let's say. So at x equals 0, remember back to the image from the screen share, or also remember that x equals 0 was a critical point. That's actually the place where you had a horizontal tangent line. So it was really easy to figure out the equation of that tangent line. The equation of that tangent line is y equals a number, and we just have to figure out how high it is. Is it y equals -1? Is it y equals 0? Is it y equals 2? How do you do that? Well, given an x, if you want a y, you always go back to the original function. So the original function, when I plug in 0 for x, I'll get 0 plus 0 plus 1/4. So that's the equation of the tangent line at x equals 0. It's y equals 1/4. And now we want the equation of the tangent line at x equals 1. Think back to our screen share. We went increasing until 0, a little more increasing to 1/3, decreasing. So at x equals 1, we're going to have a negative tangent line. We'll be decreasing. So we should expect that this y equals mx plus b, it will have an m and it will have a b. It's not as easy as this one, y equals 1/4. And we expect that the m should be negative. And then we expect the b should be positive, right? When we think back to our screen share graph of this function. So let's go ahead and do that. This will be m is f prime of 1. So here's f prime of x for any x. So I'm just going to plug in 1. So I'll have -3 plus 1 is -2. So my slope, I can fill that in. Oops. Make that a little bit clearer. Now I have an equation that I need to solve, figure out what the b value is. If I have an x and a y, I can do that. There is an x and a y that I have. I know when x is 1, that's actually the point of tangency. So I'll plug in 1 for x. I need to figure out the y, and I'll solve for b. So when x is 1, what is the corresponding y? Always go back to the function to figure that out. So when x is 1, y is -3/4. I'm going to write this one out. -3/4 plus 1/3 plus 1/4, which is -1/2 plus 1/3, which is what? -3/6 plus 2/6 is -1/6. So -1/6 goes here. Bring our 2 to the other side, becomes a +2. So we'll have 12, a positive 11/6 is what b is. So now we're almost ready to figure out the y equals mx plus b. That's going to be y equals -2x plus 11/6. Good way to check your work visually is pause the video, go to your tech tool, enter the function and the tangent line, and make sure at x equals 1, they just barely touch. But this does check all of our other visual intuition about this problem, which was that it should be decreasing there, a negative leading line. We do have a negative slope. It should have gone through a positive y-intercept, and it does. Okay, good. So next, that is critical points and intervals of increase and decrease. That's a big computational part of chapter 2. In the next video, we're going to get to review something you may not have seen since high school, exponential and ln functions, and then we'll be able to take their derivatives and add them to our list here.